Welcome back to Codex. Over the next few weeks, Codex will be the home for talks rescheduled from the 2022 JMM special session on recent advances in packing. Our first speaker is Gene Kopp. Starting this fall, he'll be an assistant professor at Louisiana State. Professor Kopp's research is in number theory, and he's particularly interested in explicit class field theory and the start conjectures. Today, he'll tell us about progress towards a constructive proof of Zauner's conjecture. Take it away, Gene.
Okay, thank you for that wonderful introduction, Dustin. So the title of the talk that I agreed on with my co-authors was A Step Towards a Constructive Proof of Zauner's Conjecture. I should be clear that we do not have a proof of Zauner's conjecture or anything that is particularly close to a proof, but I do think that this constitutes progress in that direction. So I will try to justify that claim throughout the talk. The other disclaimer is, this announces results from 5 forthcoming preprints, and there's none of these are on archive yet. They're all in some stage of very close to done to, mostly written. But there's a chance that, titles, notations, and minor details may change, and even an even larger chance that in copying things onto slides and making the theorems short enough to fit on a slide that some errors were introduced. So but I'll disclaimer over, I will dive in. The structure of this talk, the first part of the talk after the introduction will be refining Zauner's conjecture. So these will talk about the historical and new refinements of Zauner's conjecture on the existence of Sikhs. And the next section is called ghostly constructions. So these are, indirect constructions of Sikhs, and something else called MEFs via more direct constructions of related ghost objects. And this is the most technical and number theory heavy section of the talk. And I'm going to end by turning away from number theory and giving a sort of a bite-sized problem that people can, I don't know if it's bite-sized, but a problem that people can think about in kind of a new direction, inspired by these new objects that we're finding from the number theory that you may be able to find similar objects without doing number theory, just by other sorts of methods. So I'm gonna start with the basics. So this is, you can draw 3 equiangular lines in R2. You can't draw 4. If you have a set of lines, so those are, I'm thinking of those as points in projective space. You say that the lines are equiangular, the angles defined in terms of the inner product. So you can say they're equiangular if all the pairwise inner products are the same. And for complex lines, which is going to be the focus of this talk, the angle is the Hermitian angle, so the inner product is the Hermitian inner product, Vj bar dot Vk. And in terms of Hermitian projections, which I'm going to use talk about more than the lines, the equiangularity means the traces of the pairwise products of the projections are all the same. And so we can ask, going from R2 to C2, is it possible to find more than 3 equiangular lines if you allow complex numbers? And the answer is yes. There they are algebraically, and there they are geometrically. Well, why is that a picture of that? Well, the P1 of C is the same as the Riemann sphere, which is just a sphere, and you want to space 4 points out on the sphere as far as possible, so that you put them at the vertices of a regular tetrahedron. And the more general picture of complex equiangular lines is trying to embed a regular simplex into some sort of more complicated space than the sphere, which can be thought of as a quantum state space, although I will not talk about it in that way in this talk. So the first thing that was proved about complex equiangular lines was how the upper bound of d squared. So if you have so this goes back to the 70s, Delsart, Goethals, and Seidel. If you have n equiangular lines, in complex projective space, you give the most d squared of them. Here 2 squared is 4, and that also determines the angle. And the proof of this is it comes down to showing that the projections onto the lines have to be linearly independent. So yeah, and I guess the value of alpha follows from after showing that the lines have to form a tight frame. So that's so a Sikh is you could define it as a set of d squared equiangular lines, but I'm going to write it formally in terms of the projection matrices. Pi 1 to pi up to pi d squared are d by d complex matrices. They are idempotent, they square themselves. The trace of the product of 2 of them is 1 over d plus 1. They're all rank 1, meaning they're projections onto lines, and they're Hermitian, so they're they're not just any projection, but the sort of the complex analog of an orthogonal projection onto a line. And a Sikh is equivalent to a maximal set of complex equiangular lines. It's equivalent to a maximal complex equiangular tight frame, or ETF. So that's saying that there's an additional tightness condition that these projectors satisfy, and it's also something called a minimal complex projective 2 design. So it's both an example of a maximal nice object and a minimal nice object. So they've got a lot of extra nice properties that you get for free from this definition. And something a bit more general, MEFs. So if we generalize from equiangular lines to equichordal subspaces, Delsart, Griffiths, and Seidel's upper bound of d squared still holds. And a rank R MEF is going to be a set of Hermitian projections, pi1 up to pi d squared, where now the rank of the projections are R, so they're projecting onto dimension R subspaces, and the value of the trace of a product of two of them now is this fraction R times dr minus 1 over d squared minus 1, which is determined by, if you say all the traces are the same, that's what it has to be. And MEFs are so maximal equichordal fusion frames. They're a special case of equichordal tight fusion frames, and they've also been called STFFs, symmetric tight fusion frames. These are, when you move from studying equiangular lines to equiangular subspaces, there was some ambiguity in what that would mean. There were some stronger conditions, like equiisoclinic or equispectral, but those stronger conditions are too strong to be all that interesting for these maximal objects. At least that's as far as I know. So this is sort of the sweet spot where you're getting, they're interesting objects with these properties. And so I'm gonna, I'm not an expert in fusion frames. So, if you want to know more about fusion frames, maybe you should talk to Emily. So I will now, I will talk more about MEFs later in the talk. So for Sikh, I've said Sikhs have all these nice properties, so we want to know that they exist, and so the conjecture is that Zauner's conjecture, they exist in every dimension, this is sort of surprising in the sense that that for real equiangular lines, you don't expect sort of the analogous statement to be true, that that there's a natural upper bound that is usually not saturated, and sort of just by dimension counting, thinking about number of equations, number of variables, you shouldn't really expect Sikhs to exist, but they do. So there's something special going on, and Sikhs have been found in many specific dimensions, but not yet in an infinite family of dimensions. So they're known in dimensions up to 53 and many other specific dimensions up to 1299. It's possible these numbers have gone up. You could talk to Marcus Grassel for whatever his latest results are, but the numerical Sikhs, so where you don't ask for a proof that you found a Sikh, but just a numerical approximation, are known up to at least dimension 193 and various higher dimensions, and as I said, most of, I mentioned Marcus Grassel. Yeah, Marcus Grassel and Andrew Scott are responsible for finding the bulk of these solutions, although there are others that, there are a lot, other people have been in who found, some particularly interesting families of Sikhs. And so, and so by studying known Sikhs, by studying the big tables of numerical data, people starting with Zauner himself have formulated increasingly more precise refinements of this conjecture, not just saying they exist, but saying they have certain properties that might help you find them or prove they exist eventually. Right, so refining. So now we're going to move into refining Zauner's conjecture. And so for that, I need the Weil-Heisenberg group. So this is going to be, there are different ways to define it. But for me, in this talk, the Weil-Heisenberg group is going to be a particular matrix group. And so zeta is going to be a D-through of unity, and C is either a D or 2D through of unity, depending on parity. And the Weil-Heisenberg group will be the finite unitary matrix group generated by X and Z and powers of C times the identity. And it's a finite group because X and Z both have order D and C has order D or 2D. And yeah, I should say X is if you think about X and Z as operators, that X is like a shift operator and Z is like a modulation operator. And this is a special case of a more general construction, and there are infinite dimensional analogs and so on. That is very important in physics. And so a special set of coset representatives for WH of D modulo its center. So its center is just the scalars C to the K times the identity. And so these DP, which are X to the P1, Z to the P2 times this scalar C to the P1, P2. These are just a special set of coset representatives that play a special role because they have some nice algebraic properties. And they also, there are D squared of them, and it turns out that they form a basis for the set of, or for the vector space of unitary matrices, or sorry, the vector space of just D by D matrices. D by D complex matrices. So that's a a fact that will be used later. But the reason why we don't just do X to the P1, Z to the P2 is just because there are some formulas that come out nicer if you use these DPs. And so what did Zauner actually conjecture about Sikhs? So he conjectured that there's at least one Sikh in every dimension, D greater than or equal to 1, that satisfies the following properties. So first of all, it's Weil-Heisenberg covariant, meaning it's the orbit of a single projection under the conjugation action of this group, which is, in other words, you take pi and then you conjugate it by these DPs, and that gives you D squared projections, and those should form a Sikh. And so this reduces the problem of finding Sikhs to finding pi. And this definitely shouldn't work for any pi. It's a very special pi that it works for. And then secondly, there's, Zauner conjectured that pi could be chosen to be fixed by conjugation by another matrix, U sub Zau, I'm calling it. That's Zauner did not call it that, but it's an order 3 matrix. The fact that it's order 3 is related to Gauss sums. It's not trivial to check that, but this is what it has, those entries, and it can be it can be also be understood via the They representation of the SL2 of Z mod DZ, which embeds into and essentially is this Clifford group. Or it didn't define the Clifford group yet. I shouldn't say it. Sorry. There are ways to understand this as the image of some fairly simple 2x2 matrix under a representation. And so all the known Sikhs, except for one of them, satisfy 1. So there are these Hogger lines in dimension 8 that are covariant by a different group, but all of the known Sikhs except that one are Feil-Heisenberg covariant for this WH of D. And there are Sikhs that don't satisfy 2, but even up to the appropriate notion of equivalence, but there appears to be one in every dimension, or at least one in every dimension that satisfies 2. Okay. And so, so we want to refine Zauner in it first by saying Zauner says there's a Sikh in every dimension. So how many Sikhs are there? And I'm going to be a little cautious here and not say how many Sikhs are there, but say how many Feil-Heisenberg covariant Sikhs are, just leaving open the possibility that there are some weird ones that we haven't found. But so a Sikh will remain a Sikh after a unitary rotation. To talk about equivalence, or to count things, we need to know what we're counting them up to. So we don't want to count a Sikh and a unitary transformation of that Sikh as the same. I mean, we want to count them as the same, not as different. We don't want to count the rotation of something as a different thing. So we're gonna say that a unitary transformation, or an anti-unitary transformation. So a unitary composed with complex conjugation, we call those transformations extended unitary transformations, and they form the extended unitary group. And 2 Sikhs will be equivalent if they're conjugate by something in this extended unitary group. And so Feil-Heisenberg Sikhs in particular, you can use the same definition, but this definition will be it actually implies that two fiducial projectors are equivalent if and only if they're conjugate by something in this smaller group, the extended Clifford group, which is a finite group, and which is it's the normalizer of WH of D and EU of D, and can also be thought of as the image of some representation of SL2 Z mod D along with so semi-direct product of the Weil-Heisenberg group. So there's it's a well understood group, but and it's importantly it's finite. So
Gene,
yeah,
finite modulo scalars, is that what you mean?
Yes, sorry.
Okay, still checking. Thank you.
Yeah. Oh, okay. Hold on. Yeah. Okay. Yeah. I mean finite modulo scalars. All right. So all right. So something funny happens when D equals 3. You get infinitely many Sikhs in dimension 3. There's a continuous family, but when D is not 3, we expect that there are finitely many Weil-Heisenberg Sikhs up to this EC of D action. And so the conjecture is that you can count them by binary quadratic forms. And so this conjecture appears in a slightly different form in my PhD thesis, and is the inspiration to look at this, this discriminant delta equals D plus 1 times D minus 3 is came out of Appleby, Fleming, and McConnell and Yard's earlier work, which I'm going to talk about in a minute. But in terms of just counting how many Sikhs there are, this appears to be the right answer. I've looked at, it's been checked up to dimension 90 with Scott and Grassel's solutions, and so here the left-hand side is number of Weil-Heisenberg Sikhs mod ECD, and the right-hand side is binary quadratic forms of just this discriminant delta modulo change of basis, where you multiply by the determinant of the change of basis matrix. And this quantity on the right-hand side, you can also think of it, if you want, as the number of GL2Z conjugacy classes of elements of SL2Z of trace D minus 1. So that's a way to think of it, that where delta doesn't even show up, which is kind of nice. And you can also think of it as and this is how I originally thought about it, as a certain sum of class numbers of real quadratic rings. Yeah. Okay. And so now we're going to get into the serious number theory to introduce to, to talk about the fields over which Sikhs are defined, the entries of pi presumably live. So now we'll let K be a number field, and OK is its ring of integers. And so if you don't understand all the details of this, it won't be necessary. It won't, it's not necessary that you understand all the details, but the idea here is, these are some groups that are defined in terms of parameters M and sigma. M is an ideal in a number ring, and sigma is a subset of the real embeddings of K. So it's a finite set of maps from K to the real numbers. And this is the class group without the word ray is fractional ideals modulo principal ideals, and it's and this is a larger group where for technical reasons you have to put coprime to M in the numerator, but you all the more important part here is that you're modding out by fractional ideals generated by something that's one mod M and positive at these real places. So this is a technical construction of some abelian groups that are defined by data intrinsic to the field K, and you can associate to these groups. You can associate fields to these groups, and that are extensions of Galois extensions of K with these Galois groups, which are abelian groups. So, and they satisfy a bunch of compatibility relations and other nice properties. The triumph of class field theory is that you can construct these fields and vary M and sigma and generate all the abelian extensions of K this way. And so I guess by construct I mean abstractly define them in a way that isn't necessarily practical. But but the point is that if you were interested in the question of what are all the Galois extensions of K that are abelian, this is the abstract answer to that question, and it has a very nice description in terms of intrinsic data to K. So this is a very important piece of algebraic number theory that may not be totally motivated in this context, but for what we actually want to define the fields where Sikhs are presumably defined, we actually need a slightly larger class of fields, and so this is so Jeff Lee Aries and I had to define these ray class groups and ray class fields of orders, where instead of the OK, the ring of integers, you have O, which is an arbitrary order or an arbitrary full rank subring of K. And so you modify the definition by putting O in there and demanding that your ideals are invertible, which is something that's automatically true in for OK, because OK is a Dedekind domain, but isn't true for these orders in general. And then this is generally a larger group than the CL M sigma of OK. And there's an associated ray class field, which you get just from classical class field theory by relating these new class groups to the more standard ray class groups, and this notion interpolates between ray class fields and something called ring class fields, which are associated to orders. And so I will now move back and go back to Sikhs. So this is the conjecture for where the entries of a Sikh live. So again, D will not be 3, and delta will be D plus 1 times D minus 3. And now we're going to write delta as F squared delta naught, where delta naught is as a fundamental discriminant. So it's either square free or it's 4 times something square free, where that square free part is not 0 or 1 mod 4. So there's, so this, what's written so far is equivalent to the previous conjecture. So it's just saying that there's a bijection between this set of quadratic forms up to equivalence and the set of Weil-Heisenberg Sikhs up to equivalence. But rather than saying the sizes are the same, I'm saying more suggestively that there's a bijection, and which is technically the same, but now I'm going to say some additional properties that bijection has. It's sort of stratified by this conductor F prime, which is you write your quadratic form Q, you factor out the greatest common factor of the coefficients, and you write that as a fraction F over F prime, where F is this largest square, or this square factor of the discriminant. Then the entries of pi, your fiducial projector, the conjecture says that they live in the ray class field of associated to, I'm trying to highlight, but it won't let me, associated to the order O, and the modulus DO and one of the real places. So here what I want to draw your attention to is that this order O involves this F prime, this conductor. And if you look at just the pi q associated to a fixed F prime and a fixed delta, they should be Galois conjugate to each other, and this Galois conjugacy property and the connection to ray class fields was observed by, I believe, Fleming, McConnell, and Yard back in 2016, but they didn't have the language of these ray class fields of orders, so that this precise form of the conjecture was only for f prime equals 1, but now we have these Ray class fields of orders, so we can state this for all known families of Weil-Heisenberg Sikhs. And so, so now back to number theory for a minute. This is more of a high-level discussion. Hilbert's 12th problem is one of the famous Hilbert problems, and it asks for an explicit construction of abelian extensions of number fields, abelian Galois extensions using special values of transcendental functions. And this problem is motivated by the beauty of the known constructions. So in the case of the rational numbers, abelian extensions are cyclotomic fields, and so it's very simple. They're generated by cyclotomic fields are generated by roots of unity. And the values of the complex exponential and rational numbers. And this is the Kronecker-Weber theorem, says that all the abelian extensions of Q are subfields of cyclotomic fields. And then there's a beautiful theory of complex multiplication of elliptic curves and CM values of modular functions that describes what happens for imaginary quadratic base fields. And the Hilbert's 12th problem is considered such an important problem, partially because like this theory of complex multiplication is just so beautiful that there must be some sort of generalization, but no one's found it yet, or they found pieces of it, but not the whole theory. So there are geometric interpretations for the circle or for an elliptic curve, a CM elliptic curve, and Sikhs are geometric. So Sikhs hint at some as yet unknown geometry governing class field theory for real quadratic fields. But there is an issue here that you only get a restricted set of class fields. There's this dependence between, there's relationship between delta and d. Delta the discriminant, and d the dimension, which is also the modulus of the Ray class field. And so to uncouple that dependence, we look at maths. For these higher rank analogs of Sikhs. And so here's the main conjecture for maths. Again, I think instead of d does not equal 3, that should say r does not equal d plus or minus 1 over 2, because those are the cases when you get an infinite family. And we're going to suppose that d squared minus 1 divides r times d minus r, and call that ratio n, and then we define delta in terms of n. This is the same delta in the case r equals 1 that we had for Sikhs, but it's in general you get other of pairs d comma delta than you got with Sikhs, and so, right, delta is f squared times delta naught as before, and we predict some sort of bijection between quadratic forms and Weil-Heisenberg covariant maths, and essentially it's the same properties here that the entries of your fiducial projection lie in a particular ray class field, and the pi q associated to a fixed conductor are Galois conjugate to each other. The difference is that these are different ray class fields than you got before, than you get for Sikhs.
Gene, can I ask you a question real quick?
Yeah.
So I'm thinking, is this meant to extend the case where r equals 1? I'm just looking at where
Yes.
you wrote n. So I'm wondering if at the top of that fraction is supposed to go the other way, if r equals 1, where n equals
Yes, that
1.
fraction is supposed to go the other way. So it's
Okay. All right. Thank you.
So that should be d squared minus 1 over r times d minus r. Sorry about that. Yeah, because that is not, that is 1 over the thing that I mean. So the first non-trivial case is do r equals 3 and d equals 11. And then you get n equals 5 in that case. Right, okay, and so now I'm going to talk about constructions. So this is a construction of, so this isn't a construction, this is a definition. This is the ghost objects that I was talking about. So a rank R ghost math is again, it would be a set of D by D matrices. So this is the same as the definition of a meth, and when R equals 1 is the same as definition of a Sikh, except that I've taken this Hermitian condition and changed it to something else. And so the new condition is that the conjugate transpose of phi j is up times phi j, where up is the following D by D matrix, which is called the parity operator. And if you think of how it acts on the index, if you think of the index of the basis for C to the D from 0 to D minus 1, it's sending the basis vector J to basis vector D minus J. So it's and so it's also UP is also the sum of the DPs, the displacement operators DP, the sort of special basis that comes from the Weil-Heisenberg group. So that's another way to think of it. Or I guess the sum of divided by D. Okay, so
hey Gene, I'm confused in the special case where phi j is rank 1. Is phi j I think of it as a rank 1 projection when r equals 1?
Yeah, so it's a projection, but it's not a it's a projection, but it's not a Hermitian projection. Yeah,
oh, it's ghost. Thank you.
This is yeah. So it's I generally use the word idempotent in case people get confused about, it's in the sense of linear algebra, it's a projection, but in the sense of, Hermitian geometry, it's not a projector.
Yeah, I somehow missed that the word ghost appears like 4 times on the slide. We're good.
So these are the ghosts, and in the rank 1 case, they're ghost Sikhs. Sikhs. Okay, and so the sort of point of ghosts, or the reason why we're studying them is that there seems to be a one-to-one correspondence between Sikhs and ghosts, and so specifically, what we can show is that if you assume the class field hypothesis, meaning that you have to assume here is that the fiducial projectors of Weil-Heisenberg Sikhs have entries in some abelian extension of Q adjoins square root of delta. Then there's a one-to-one bijection between Weil-Heisenberg Sikhs and Weil-Heisenberg ghost Sikhs, given by a choice of Galois automorphism that switches the sign of the square root of delta. And the bijection is literally given by you write down let's say your ghost Sikh, and then you apply the Galois automorphism. You write it down algebraically, and then you apply the Galois automorphism to all the entries, and then you have a Sikh, or a Sikh projector. And I think that this will all carry over to MEFs, but we haven't actually done it. Okay. All right, so now we get into some analysis. So we're gonna this is a special function. So I mentioned special functions in the context of Hilbert's 12th problem, and this is I'm going to define a candidate special function to generate abelian extensions of real quadratic fields. And so this pi sub r, this is a var pi sub r of tau. And this is, it's defined via this infinite product, and this, I'm realizing now that this is not quite correct as written. This group SL2Z should actually be a congruent subgroup of SL2Z that depends on the denominators of the entries of R. So and P1 should be R sub 1 and P2 should be R sub 2. Oh, sorry about that. And so, but the point of this is that this is some sort of function that is defined for tau with real part of tau greater than 1. So tau in the upper half plane, and it's what I've been calling a wannabe modular form. It transforms kind of like a modular form with some weird multiplier factor that is some crazy transcendental function, but has the property that it extends analytically beyond the upper half plane. So tau in the blue functions is in the upper half plane, but tau in the red function is in C minus a half line. And the map sending your matrix A to this function, so it's like a map to a function space, is called the Shintani-Faddeev modular cocycle, and is based on this function is related to the Shintani's double sign function and Faddeev's Faddeev's quantum dilogarithm, or non-compact quantum dilogarithm, and also to recent work of Sarkisian and Spiridonov, and it's related to it shows up in conformal field theory and as well as in number theory. It's a very, very interesting function. So,
hey,
yeah.
Is that var pi function, is it formal, or does it converge, or what? How do I think
everything that is a convergent product for a tau in the upper half plane? So it's a complex analytic function.
Got it. Thank you.
Nothing is formal. Yeah. And okay, and so the conjecture is that these things generate ghost Sikhs, and more. This function, the special values of this function of this co-cycle generate ghost Sikhs and ghost MEFs. And so that and again should be the other way around, d squared minus 1 over r times d minus r, and delta is as before, and q is some, this should say c at y squared in q delta. And so that you take a quadratic form and you take a root of that quadratic form, and you associate a particular matrix B to the quadratic form. And we look at the smallest power of B in a particular subgroup gamma of D of SL2Z, and you define nu P in the following way. So it's R when P1 and P2 is 0, and otherwise it's the following expression that is some root of unity depending on your matrix and your quadratic form, times this value of this special function, this Shin function, Shintani-Faddeev modular cocycle. And these nu P's are used to define a matrix phi, which is we conjecture to be a fiducial idempotent of a rank R File-Heisenberg ghost MEF. Yeah, so this is I'll correct the typos on this slide and post a corrected version at some point.
You should maybe just mention with.
What's that?
You should maybe just what mu.
You're breaking up. I can't hear what you're saying.
Mu.
Mu. Oh yeah, mu. Mu is something I didn't have space to define. It's the Rademacher invariant of A. It's not all that important what it is, because it's just, this isn't, it's a constant that only depends on the matrix A. So it's the same constant in all of these nu P's, but it's just, it's an integer and say that can be defined from the matrix A, and so this is a particular 24th root of unity that's showing up here.
So you just have the number 24 just hanging out for every construction?
Well, Yeah, but it was hanging out in the Zauner matrix earlier. It's hanging out in a lot of places. It's just, yeah, this is.
Should I think of the number 24 as significant, like I've seen it before?
Yes, you should. But the significance, I mean, it has a lot to do with the structure of SL2Z and yeah. So
Can I ask just a few more, because I'm not sure I caught all of the notation. Maybe you said all of this already.
Yeah.
It says smallest positive power of B and gamma of D. What is
so
gamma of
yeah. So gamma D is the congruent subgroup of all D by D matrices that are congruent to congruent to the identity modulo D. So it's
okay, and then thank you. And then I'm sure you said this, but I already forgot. In the definition of Q, so the very last thing that appears there is like cal Q of delta. Can you remind me what that is, please?
That's supposed to say is an element of Q of delta, and that Q of delta is this set of quadratic forms of discriminant delta, of binary integral quadratic forms of discriminant delta.
Okay, thank you.
Okay. Yeah. All right. So I wanted to state this precisely, but I know it's too much to absorb. So it's partially to give you to show that it is a explicit construction rather than necessarily for you to absorb everything in the talk. But yeah, the core point here is that these new P's, which are also called the overlap phases, or the overlaps, I guess, are being constructed from the special values of the Shin function, and then their number theory conjectures that will tell you that these numbers should be algebraic, and the Sikh itself, or the math itself, will be then constructed by taking a Galois automorphism, applying a Galois automorphism to these numbers. So these special values are called real multiplication values, and they're related to special values of derivatives of L functions, and the star conjectures predicted that these values live in particular abelian extensions of Q adjoining square root of delta. And so here, so if you assume, so this is just stating the theorem that we can prove, which is, you can distill the key property that you need this Shin function to satisfy as a conjecture. I'm not going to state in these slides the twisted convolution vanishing conjecture, which is a particular family of identities for these real multiplication values that essentially comes out of the idempotency condition, but can be rephrased as something being zero, which seems like the sort of thing that might be easier to prove than something being idempotent, but is at its core, basically asking for the phi squared to be phi. And so, you distill that conjecture down, and that, if you assume that, you can, then the conjecture on the previous slide is true. You get all the other properties of a Sikh, like, for example, that these numbers are real. You get that out of the connection to L values. That the the overlaps are real, which implies that the ghost overlaps are real, which implies that the Sikh overlaps are in the unit circle. So if you then make a further assumption, which is the Tate's refinement of the real quadratic rank 1 star conjecture, then you would get you get the strong form of Zauner's conjecture. So this is the conditional result, assuming both this twisted convolution of Anderson conjecture, which we don't know how to prove, and the star conjectures, which we also don't know how to prove. Yeah. Okay, and so I will say briefly, I know I'm going over time, so there is an algorithm for generating Sikhs from MEFs, which we call necromancy, because you're taking a ghost and bringing it to life, and so you generate, let's just say, a Sikh a ghost Sikh, using L functions and using the Shin function, and then you boost the precision with Newton's method, and depending on what your goal is, you either compute all the overlaps exactly, or a subset of them, using lattice basis reduction, and you compute them at a power basis, which allows you to apply a Galois automorphism, and then you can if you computed all of them, you can reconstruct the actual Sikh exactly, and if you computed enough, just some sufficiently large portion of them, you can do a numerical reconstruction using a sort of a low ranks matrix reconstruction algorithm, which works best in the case of Sikhs because they're rank 1 as opposed to rank R. And some new computational results. So this Steve Lamia is really the expert on this algorithm, but we've computed all 4 predicted Weill-Eisenberg Sikhs in dimension 100, and we've computed a number of ghost MEFs and deghosted the smallest non-trivial example with dimension 11 rank 3. Okay, and I'll go through this, and so that my challenge to anyone who wants to take it is to think more about MEFs outside of the context of this particular family of MEFs that is coming out of class field theory. So this is the definition of a MEF for reference. And there is a actual known infinite family, which is actually really simple. And in this paper I'm citing, they're called STFFs. And you can find they exist in rank D plus or minus 1 over 2. And they're a weighted average of I and UP, or possibly with a minus sign if you want rank D minus 1 over 2. And as with Sikhs in dimension 3, there's expected to be, but not proven to be, a continuous family in this rank Weil-Heisenberg MEFs, and this Wigner MEF, this really special one, generalizes the Hasse-Sikh. So these are, the actually known families, and then we have the known in quotation mark families, which are the ones that I've talked about already. So again, I've got the fraction the wrong way around. But yeah, these are the, just to give you a sense of, how common these are. Well, they exist in dimension, or they conjecturally exist in dimension 11, 19, 29, 41, 55, and so on, with the following ranks. And there are infinitely many pairs corresponding to each ratio n, but only finitely many for each rank. For example, there are none of rank 2 in this family, or this hypothetical family. Okay, and so my challenge is, we know about the Hauger-Sikh, the Hauger lines, which is group covariant for a tensor product of 3 Weil-Heisenberg groups. And if you think about the sort of most natural generalization of this for Sikhs, just tensoring more, copies of WH shoe together, you don't get other Sikhs from that from that group. And this is currently the only known MEF, as far as I know, that, unless these have been studied under a different name by someone else, that isn't covariant for WH of D. And so, but to my knowledge, no one has looked through these. No one has sort of thought that there is some rich family of these maximal fusion frames to be studied. So and I think it's a place that someone should look. And I'm too busy to do it at the moment because I have to finish all these papers. So I encourage you to, if you want, if this appeals to you, to look for MEFs that are covariant for other tensor products of Weil-Heisenberg groups or for other groups. And so I am gonna conclude there. Sorry for going over, and thanks for listening.
All right, thanks for the talk. I'm gonna react with this button here. And